Ana Villanova. I'm professor in visual analytics at the Eindhoven University of Technology, and I have the pleasure to be the chair of this session today. So today we have a state-of-the-art report in neural fields in visual computing, which is, in my opinion, a very exciting and a very hot topic nowadays. So the amount of publications in this direction is really exploding. So it's very nice to have such a work to summarize what is going on. So really looking forward to the presentation. This has been, so this is a joint effort for many authors and also institutions. So Brown Computer Science, MIT, Munich University of Technology, University of Toronto, Unity, NVIDIA, Meta Reality Labs, and Google Research. So many main players in the field are actually represented here. So the session today will be given by two speakers. So Yihan Xie. So he's actually an undergraduate student right now at Brown University Research, and also he's a scientist at Unity Research. His research interests include 3D reconstruction, neural renderings, and reinforcement learning. And he's going to start his PhD in Caltech soon. Our second speaker will be Towaki Takikawa, sitting here. So he is a computer science PhD at the University of Toronto. He is also research scientist at NVIDIA and at Hyperscale Graphics Systems Research Group at the Hyperscale Center. His research interests are broadly spanned in computer graphics, computer vision, and machine learning. So they will be the speakers of today. So Yihan will be starting. We have agreed with the speakers that actually questions can be asked through the session. We will try to keep track of time such that we are sure that we end on time, but we think it's more adequate for such a long talk that people can ask questions in between. So if you have a question, just raise your hand. We have also people online, so we have to give you the microphone such that the people with whom we are streaming can also hear the question. So please just raise your hand and we will give you the microphone. Say that, I want to give the floor to Yihan.
Thank you, Dr. Villanova. Good morning and welcome to the State-of-the-Art report on neural fields in visual computing. I'm Xie Yihan, and together with Towaki today, we'll talk about neural fields, an emerging technique that has gained significant popularity in our visual computing community. In the next hour, we'll first define what are neural fields, why they're so popular, and how the neural fields enable state-of-the-art applications. We've designed this talk to be accessible to non-experts, so sit back, let the champagne last night do its magic, and enjoy this talk. What is a neural field? A neural field uses a neural network to parameterize a scalar or vector field. These vector fields can represent physical quantities like the magnetic field or velocity of a fluid. At every coordinate position in space, the physical quantity is well defined, whether it is the magnetic field strength or the velocity of the fluid. Here's a familiar example in computer graphics. Fields can also represent geometric quantities, such as the sign distance function, SDF, which is a function that outputs distance to the nearest surface, given the coordinate in space. These vector fields can also be geospatial quantities, like statistics about crime, poverty, population density for a given position on a map. Any real-world signals can be described as a field, and all of those fields can be represented by a neural network, with taking coordinates as an input, making them neural fields. Many influential works have already appeared in visual computing. For example, neural fields have enabled 3D reconstruction from cell phone images. While this is already impressive, there are also obvious issues that we can see here. Neural fields can also learn from data and represent human bodies or faces, or even faces of cats. These are only the tip of the iceberg of the hundreds of works published in the past 3 years using neural fields as the underlying representation. Beyond graphics and vision, neural fields have also proven to be useful. In robotics, neural fields can be used to describe object geometry for robotic grasping tasks. Fields can also be used for navigation using visual input only. According to the explosion of neural fields in visual computing, a similar popularization of neural fields was taking place in the computational physics community. Neural fields have been applied to topology optimization, homographic reconstruction in medical imaging, astronomy, as well as contact dynamics between objects. Again, these works are only a tip of the iceberg, a very small subset of all the research that has taken place in the past few years. Fields have also pushed the research community to develop a more rigorous theoretical understanding of neural networks themselves. The neural networks used in many applications require special properties different from applications in deep learning. One of such desired property, for example, is fitting high-frequency signals, which is difficult due to neural networks' spectral bias. Reaction and excitement from the research community on neural fields have been huge. The number of publications using neural fields have been growing exponentially. In the past 3 years, we saw more than 400 papers using neural fields. Here are some of the influential works. Again, just the tip of the iceberg. Of our knowledge, neural fields was first introduced in 1998 in Eurographics. Neural network here was used to parameterize the bidirectional reflectance distribution function of the RGF. Again, 24 years from today. What is so great about neural fields, and why are people using them in so many application areas, and why do they provide state-of-the-art results? No single paper makes this crystal clear. Researchers are actually debating over these questions all the time, and meanwhile, we see dozens of new papers in our inbox every month overwhelming us. Thanks to this Cambrian explosion, answering those questions requires reading hundreds of papers. In addition to that, the different proposed terminologies have also confounded our community. We have seen concurrent and repeated works, and it has become difficult to consolidate and disseminate ideas on this topic. So someone has to read all those papers and distill a taxonomy of these related topics so we can approach neural fields with consistent terminology. This is what motivated us to write this state-of-the-art report. And in addition, we built a website database of all neural fields papers so you can easily keep track of the latest developments. You can visit our website today at neurofields.cs.brown.edu. And to drive the point home, we've prepared a funny Easter egg video for you all to wake you up. Academics are known for our great sense of humor. Also welcome questions throughout the presentation, as we said. There'll be several mini breaks in the next hour where we'll introduce some features of our website. So let's take a look. We can explore hundreds of neural fields papers using our search and filter feature. We can create filters by a particular author, particular keyword, a particular conference or journal, or between a specific time frame. You can also combine these filters to create your custom filter. And if you only want papers with code, you can do that, checking this box. If you want to show peer-reviewed papers and filter out the arXiv papers, you can also do that. And finally, you can export all the BibTeX citations of all the papers you're interested in. Only some of the things we can do, with more to be shown later. The talk will consist of 4 sections. We'll first introduce what a neural field is. We'll then spend around 10 minutes motivating why neural fields are useful. And then the bulk of this presentation will focus on the techniques that make neural fields powerful. And then we'll spend around 15 minutes introducing several state-of-the-art applications of neural fields. Let's start with introduction. formally define what is a neural field. The definition of neural fields is derived from physics. A field is a quantity defined for all spatial and/or temporal coordinates. The quantity itself can be a scalar or a vector. Now we define neural field to be a field that is parameterized by a neural network. The clean and elegant definition that identifies a class of neural networks with very similar properties. These are essentially two criteria. One, is there a neural network? And two, does the neural network take coordinates as inputs? To visualize this definition, here are some examples, such as gravitational field mapping spatial coordinates to acceleration, an explicit surface in 3D mapping 2D coordinates x and y to a height z, sign distance field, images, as well as audio signals. And they can all be neural fields if we parameterize them with a neural network. Some comments. First, although the most common types of coordinates are spatial temporal, neural fields are really not restricted to these types at all. For example, neural fields can also take coordinates in the frequency space. In addition, although our definition does not restrict the type of neural network, in practice, the neural network is almost always multilayer perceptrons, or MLPs, because they are universal function approximators. And questions? My professor used to say, if there's no questions, it means either everybody understands everything or nobody understands nothing. So I hope it's the former. Okay, that's great. Having a number of proposed terminology as well as some misnomers. For example, the term implicit representations is derived from implicit surfaces in 3D geometry. And implicit surfaces are level sets of a scalar function, as opposed to explicit representations, such as point clouds or voxels or meshes. The term implicit representation is accurate when we talk about sign distance function, occupancy, for example. The term is not appropriate when the neural field parameterizes 2D images, for example. Coordinate-based neural network is another term. It is accurate, but a bit of a mouthful. And another common term is NERF, or neural radiance field. This is often used correctly, but it is restricted to a specific class of neural fields that parameterize the radiance of points in space. Considered all of those proposed terminologies and recommend neural fields as a terminology that reflects the underlying architectural similarity shared by all of those neural networks. With that, we now answer the question, why do we want to use neural fields?
Thanks, Yang. Why should we use neural fields? First of all, neural fields inherit a lot of the properties of traditional field representations, for example, grids, like differentiability, continuity, and also versatility of being able to represent a bunch of different kinds of signals. There are a number of additional traits which make neural fields attractive. To focus our discussion, many of these traits will focus on vanilla neural fields, which use a single neural network to parameterize the field without any of the fancy techniques and components of neural fields that we'll discuss much later. In our presentation, we will focus on three factors: compactness, regularization, and the agnosticity to the input dimension. To better understand these traits, we will first review how fields and signals are typically represented in traditional computer graphics and vision. In general, most fields or signals found in the world are continuous. We can treat these fields as a function which maps from Rm, the input coordinate space, to Rn, some kind of output space. In the signal processing world, this is known as a multidimensional and multi-channel signal. Representing a continuous signal on a computer is not straightforward at all, because computers are inherently discrete, and it's not very clear how to represent these continuous functions. That is why in signal processing, we tend to represent signals as vectors. Specifically, they are represented as equally spaced samples from the continuous signal. So for example, in this diagram you see here, the green dotted line is the underlying continuous signal, and the 8 green samples that you see, these dots, are the 8 samples that form a vector. Making these equally spaced, we can use the rich theory of frequency-based signal processing tools like the Fourier transform and sampling theory. For example, the Fourier transform can take this discrete vector representation and reformulate it as a sum of different sines and cosines of different frequencies. Making them vectors, is that working? Cool. Yeah, so making them vectors, we can also use the rich sets of tools from linear algebra to perform further processing. For example, apply a linear transform on your signal to transform into some other space. Although we call them discrete, these representations can still also be continuous because you can interpolate them. Specifically, you can treat these samples as Dirac deltas, which you can apply a continuous convolution filter on to interpolate them. For example, just simple linear interpolation. Let's consider as an example an image. Images are fields with a two-dimensional domain, x and y, and a three-dimensional output space of red, green, and blue. Using a sensing device, such as a camera, we can capture images directly as a two-dimensional discrete signal with 3 channels. Cost of digital signals depend highly on the input dimension. Image pixels are generally stored as 1-byte integers, which can represent enough dynamic range of colors for the human eye perceptually. If this image is a 1024 by 1024 image, this takes up 3 megabytes of storage on your computer if you just store it as a integer array. Adding a temporal dimension for videos makes this representation a lot harder to store. For example, if you have, for example, a 2-hour movie, a single video can end up being 0.7 terabytes. Storing close to a terabyte for every movie is really not feasible, so significant research and development has gone into making images and videos compressible with different compression algorithms. Standards you might have heard of, like JPEG and H.264, are very much products of that. And videos are especially compressible because there's a lot of redundancy in the signal across the temporal dimension. For example, if you look at this, these sequence of images, between image and image, it doesn't change a whole lot. But instead of extending images to the temporal direction, we can also extend it to another spatial direction to get a 3D signal representation which stores some sort of information for every point in a bounded 3D space. In computer graphics and vision, this sort of structure is often referred to as a voxel grid. If you take an image and then extend it to another spatial domain, for example, you get a 3D signal, in this case, a voxel grid. Corners of this kind of voxel grid store useful information, or channels. So the input dimension to this signal representation, the voxel, is R3, so 3D coordinates, and the output dimension is Rn, which stores some useful vectors. This information stored in this volumetric 3D space can represent things like geometry, like sign distance functions or density. They can also represent appearance, like color or BRDF parameters, so spatially varying BRDF fields. Unlike videos, voxels usually don't have a lot of redundancy across a specific axis. So unlike videos, they are not easily compressible. There are standards for voxel compression, like the MPEG PCCG standard, but they are not very mature yet. This is a very recurring problem with voxels that you'll see a lot. They are very expensive to store and take up a lot of memory. The option which is popular in computer graphics is to use polygon meshes, which define surfaces of hard 3D objects with polygons. These are usually much more compact than voxels, and as such, they are much more commonly used in things like computer graphics. Unlike voxels though, the input space is no longer R3, and only hard surfaces can really be defined with meshes, which makes them harder to use in applications like medical imaging where you need volumetric data. Although this is a powerful representation, many things like connectivity, topology, manifoldness, self-intersections, etc. need to be considered. These things are also not very easily differentiable, so using them in a computer vision pipeline might be quite difficult. The talk later today on advances in neural rendering will likely discuss many of these factors in much more detail, so you should definitely check that talk out also. These problems, like excessive storage space of voxels and also the algorithmic complexity of meshes, are motivations for alternate signal representations like neural fields. Neural fields use a single neural network to parameterize and approximate the underlying continuous signal. Let's now discuss some specific properties that make these neural fields attractive to use. First trait that we'll talk about specifically for neural fields is compactness. So as the motivating example for all of these different neural fields traits, like, for example, compactness, we will first introduce the problem of 3D reconstruction from multi-view images. Nice example, because they follow a structure known as the inverse problem that we'll talk about a lot, is applicable to all sorts of problems, not just in computer vision, but also in things like computational physics. 3D reconstruction, we wish to obtain some sort of 3D signal which represents the geometry and the appearance of the scene. We often don't have the ability to directly measure digital signals in 3D space. So we need to infer them from something. For example, a sequence of multi-view images that's looking at an object from a bunch of different locations. The signal can be something like the geometry represented by the sine distance function, or maybe also things like appearance represented as the RGB color. And you want to reconstruct basically both of those things using multi-view sequences. You can solve these types of problems as inverse problems, where we find some kind of forward map function f, which maps the signal of interest to the signal available, and then you solve an optimization problem where we find some signal x which aligns with the observations you have available. So for example, in this case, the signal that you really want to get is 3D geometry and appearance, which is x. Then the signal you have available is multi-view images, which you took from a bunch. Basically, this forward map function f is some differentiable function that basically maps the signal you want, which is 3D geometry and appearance, which is trying to find, to find the correspondences between them and solve this optimization problem. And in this case, x, the forward map function f, can be something like differentiable rendering. The important design consideration with is this: how do we represent the signal of interest x such that we can feasibly solve this optimization problem? We reiterate, although we show an example for computer vision, this sort of a whole bunch of problems in the world can be framed and solved as these inverse problems, which we have involve basically a signal x and a forward map function f that maps to some ground truth function. One option is to represent the signal as a digital signal, which in 3D would be a voxel grid we just talked about earlier, which stores, in this case, density and spherical harmonics coefficients that model both the appearance and geometry. We could then use something like differentiable rendering to optimize for an image alignment loss with multi-view images. One example of this is Planoxels by Yu et al., which follows this exact same approach with voxels and differentiable rendering. This digital signal-based approach, by adding a third dimension to the third digital signal domain, the required memory for this approach explodes. For a relatively small single object scene, a discrete signal approach may require up to 700 megabytes to store at high quality. For very large scenes, this could be a huge problem and motivates the need for an alternate representation for 3D signals. As an alternate solution, we can also use a neural field to represent this 3D signal that we are interested in recovering instead of using a voxel grid. Since all we need is a neural network to represent this signal, we only need about 2 megabytes to store this neural network. And this example specifically is the neural radiance field. Muscle-based radiance fields as a comparison requires 700 megabytes of memory to encode scenes of similar quality. That basically means that neural fields are orders of magnitude smaller and much more compressed compared to digital signals. This, of course, does not come without cost because we never have a free lunch. Planoxyls are much bigger, but they are also much more computationally efficient in comparison to neural fields. We'll touch on these weaknesses much more later. Another trait that's nice about neural fields is regularization. Most of the time, 3D reconstruction is an under-constrained problem and I have infinite solutions. We use the word under-constrained in the same way in the linear algebra sense, where if you have a linear system with a rectangular matrix with not enough rows, then you might have infinite solutions to that linear system. Say for an example that we have two camera rays that are looking at this blue-colored bunny and you want to reconstruct this bunny. The correct image space reconstruction would give us a blue bunny with this exact geometry, and it would give us perfect reconstruction laws according to the image space laws. This, however, isn't the only solution that you might get from this kind of reconstruction laws. You could also have a spurious reconstruction, for example, this like blue sphere that you might see. If you just look at the image space laws based on the two camera rays, you would get the same exact laws as the blue bunny. So this basically means that two rays doesn't seem like it's enough to actually constrain this problem such that you can actually feasibly solve this problem in the first place. The solution, of course, is to have a lot more ground truth such that you can fully constrain the system. Maybe in addition to rays looking at the bunny, you also have rays looking at the background and at different angles and all sorts of different locations. If you can have this for every location possible, you can probably just carve out space to basically find this blue bunny. This, however, is a lot of times not feasible or expensive because maybe your application is something like single view reconstruction, or maybe you have some SLAM system where you can't just take that long to scan an object or something like that. The solution to this is to add to your inverse problem formulation a regularization function P. We generally need this kind of regularization because the system is under constraint, and you need some additional knowledge or some priors about how the system behaves in order to constrain the system such that you can solve this problem, even if you have an under constrained system. Funny example, for example, maybe we know the object is a bunny, and we have some function which can encourage the signal to be more bunny-like. In a more classic linear systems kind of example, this regularization function might be such as something like L2 or L1 regularization or something like that. General setup is also known as compressed sensing. Approaches which use digital signals to solve under-constrained problems often require regularization. In planoxyls, for example, which uses a digital signal, they need to use total variation regularization to solve the shape radiance ambiguity problem. As you can see from the results, basically not using TV regularization will result in a lot of spurious reconstructions. The total variation regularization basically constrains the signal to be smooth. Neural fields, on the other hand, are not necessarily immune to this ambiguity problem, but neural fields can also solve the same inverse problem without having any additional regularization terms to balance. The architecture of the neural fields themselves itself seems to function as regularization, making reconstruction and research easier because your neural network will likely converge to a better solution easier. This is nice also because that's just one less hyperparameter you have to also choose. In some cases, neural network regularization also seems to converge to even more desirable results than using regularization. In this work, an untrained neural network was used as a prior for compressed sensing, and basically it shows that compared to TV regularization, which is the three columns in the middle, and the neural network-based solution is the one on the right, you basically see that the neural network seems to converge to a nice solution that looks perceptually nice. Of course, this isn't to say that neural networks do not benefit from things like regularization or data-driven priors. And we will discuss these things in much more detail for neural networks much later when we talk about generalization for these things. Lastly, the last benefit is that neural fields are domain agnostic. We generally think about 3D scenes as being 3D signals, but actually in reality, this is not entirely true. Since we can move around in 3D, we also need to consider our viewing direction. Materials in the real world, like mirrors as an easy example, are viewpoint dependent. As such, to model 3D scenes, we often need to consider the 5D planoptic function, which also includes information about the viewpoint. So for example, the planoptic function's input domain might consist of the 3 dimensions for the location of the eye, also the 2 more dimensions for the viewing direction. We alluded to this earlier, but this can be a huge problem for digital signals because the costs depend highly on input dimensions. The digital signals scale very fast in memory by the input dimensions, so we can't just casually add input dimensions for digital signals. Things like videos and voxels were already large. Imagine how big the 5D planoptic function or the temporal 6D planoptic function would be. Computer graphics, to deal with this, we sometimes model the different dimensions separately. For example, we can model the 3D portion of the signal with a 3D grid, and then the 3D grid then stores coefficients of a spherical basis function to encode the remaining 2D view dependence. There are solutions that exist for things like planoptic functions, but in the general case, to handle this, you always need tailored solutions. In comparison, neural network layers generally consist of matrix multiplications, which makes it really easy to add input dimensions. In this case, we obtain a 4-dimensional hidden dimension by multiplying a 2D coordinate xy by a 4x2 matrix. Adding an additional input dimension z, this course simply consists of adding a single column to that initial linear map. This means that the cost of adding an additional input dimension to neural fields is all effectively O1. We can enable lots of creative research to happen in neural fields by unlocking the input dimensionality constraint. For example, in nerve text, the cone radius of rendering is used as an additional input dimension to the neural field to control level of detail. Beyond the input dimension, neural fields also have another benefit related to being domain agnostic. Digital signals like grids have a spatially bounded domain. So, to define any sort of signal, you need to know a priori what the spatial extent of this domain is spatially. This can be quite annoying for things like 3D, where you might be looking into the sky and the spatial extent might be huge and hard to model. To get by this, you could make it cyclic, for example, but that enforces, really unflexible constraints that are hard to deal with. In comparison, neural fields are just functions that take in an input position and will adapt to your data. So neural fields are not necessarily entirely bounded by space, and this flexibility can often be really useful for modeling things in 3D, like, for example, if you want to model viewpoints going into the sky or something like that. Not a lot about benefits about neural fields, but neural fields, of course, are not perfect. Neural fields can be quite computationally expensive, especially for high-frequency signals. Neural networks in general exhibit something called spectral bias, which makes it hard to fit high-frequency functions at all. They are also not easily editable, and modeling things like semantics and discrete things with neural fields can be quite difficult sometimes. In fact, lots of neural fields research and methodologies that we will highlight in the following presentation were developed precisely such that we can address these problems with neural fields. In the next sections, we will cover these weaknesses and also some solutions for these weaknesses in much more detail. But in the meantime, we'll take any questions and maybe also take a short break.
With more questions, I have another short break looking at the project website a little bit more. If you're interested in one specific paper, for each paper in our database, it has its own homepage with many useful information such as link to PDF, text citation, the link to open source code, paper's abstracts, and the very powerful citation relationship with all the other papers in our database. You can follow up the citation tree go down the path as far as you would like. Links to open access data is provided if they exist. Project webpage from the authors, as well as the presentation video from the authors are also there if they exist. Again, lots of information at your fingertips here if you need them.
I guess we will now move on to the common We'll now move on to techniques for neural fields, which address a lot of the weaknesses we just mentioned. The first thing we will discuss is the neural network architecture. One of the classic problems with neural networks is that they are biased to fit lower frequency signals. For things like machine learning, this is actually something that's nice because it actually helps with generalization. For signal fitting, however, this can be a big problem since our goal is to fit complex and high frequency functions, often with as small of a neural network as possible. A number of different mechanisms have been proposed to address this problem. One class of these kind of mechanisms are input encodings, namely positional encodings. Positional encodings embed coordinates into axis-aligned sinusoidal waves at multiple scales. They were originally used as a way for embedding positional data for sequential data like languages and animation so that they have some awareness of where you are on this sequence of data, basically. But they were also adopted in neural fields as a way of input, as an input embedding that can basically found out that it can also alleviate spectral bias. The input embeddings also exist, and they have much more, being proposed every day. Random Fourier encodings, for example, are kind of like positional embeddings, but instead of embedding positions into these axis-aligned signed embeddings, they embed them into non-axis aligned random directions. Some other encodings use non-sign basis functions, for example, encode positions as Gaussian embeddings. All these different kinds of positional embeddings all promise different kinds of benefits, but right now, we still don't really seem to have a really good understanding of why all these different properties emerge. So we think that this is very much open research question right now. It also works, which try to learn an optimal learning scheduling algorithm for positional encoding. Since these are hierarchical different scales of sign positional encodings, you can basically schedule your learning such that you learn the lower frequency components of the positional encoding first, and then schedule it such that you gradually learn the higher frequency details. Also, not all input encodings are actually meant for even addressing the spectral bias, which is very interesting. One example is the integrated positional encoding from MIPNERF, where the sinusoidal embeddings are adjusted dynamically according to the cone size of rendering. This allows them to basically learn a multi-scale signal, which can be filtered on the fly, and anti-alias, similar to NERF text also. This can be really useful for learning level of detail representations for computer graphics. Also attempts to solve the spectral bias, not with a positional encoding, but by using different activation functions. Activation functions are key components of neural networks. They basically refer to the nonlinearity functions placed in between neural network layers, and is a key part of enabling the universal approximation theorem of neural networks, which basically says that these nonlinearities can really help with learning really useful representations. Standard and popular activation functions include things like the sigmoid function or the Rayleigh function, which is essentially a gating mechanism. Many papers propose to replace these standard activation functions for neural fields applications. One example is Siren, which replaces the Rayleigh activation function with a sign function with a specifically catered network initialization method, and they basically show that it can fit higher frequency functions better, and also can reason about higher order gradients better, so you can also fit higher order gradients of functions better. Other works also propose a whole bunch of other activation functions. A lot of them basically show that some of these other activation functions can be useful because it's more robust to different random initializations of the network weights. Neural works attempt to also explain the behavior of these activation functions, both through theory, but also through empirical analysis. For example, if you look at these comparisons of the ranks learned by these different representations, you can see that something like Siren can successfully learn a high effective rank representation compared to conventional activation functions, which might explain something about being able to fit higher frequency functions. In general, there's still not a lot of research being done in really understanding these activations and additional encoding functions, and most of the research done is rather empirical and somewhat ad hoc, and hence we think that this is actually a really exciting research opportunity for people who want to uncover the secrets of these mechanisms. Also works which try to basically fundamentally change the structure of the neural networks to learn representations which are useful for various tasks like filtering and editing. For example, multiplicative filter networks is a frequency space representation which allows applications like explicit frequency space filtering of signals, like for example in baking, where they can basically directly edit the Fourier spectrum of this signal and basically use it for filtering at level of detail. We also talk about hybrid representations, which are very related to the network architecture as well. Although mechanisms like positional encodings address the spectral bias, they also don't address another important problem in neural fields, which is that they are very computationally expensive. Whereas positional encodings are mostly parameterless, static embeddings of the input space, hybrid representations are parametric embeddings of the input space. This basically means that the parameters of the embedding are learned simultaneously with the neural network. And it also means that the embedding itself has parameters that can be learned. Specifically, hybrid representations use something called a feature grid as the parametric embedding. These feature grids are digital signals which store features. And hence, because this is a hybrid between digital signals and also neural fields, we call them hybrid representations. And we call them digital signals. These could be things like voxel grids. They could also be things like sparse voxel grids, or things like octrees and BVHs, and all these different kinds of spatial data structures that can store features, basically embed your space into some kind of like geometric space. Since these parametric encodings do most of the heavy lifting for the learning, we can use an extremely small neural network, which makes inference extremely fast. For neural geometric level of detail, NGLOD, for example, they use this to perform neural sphere tracing in real time. These parametric encodings also solve the spectral bias to an extent by providing a high frequency structural prior to the high frequency feature grid. There are caveats to also using these hybrid encodings because which is that we lose some of the compactness of the neural network in exchange for compute. There's also an additional cost in maintaining these traditional data structures. For example, things like octrees, for example, can be sometimes hard to manage especially for graphics applications and real-time applications. One interesting research focus in the world right now is how we could inherit the benefits of neural fields like compactness, but also get the benefits of computational efficiency from things like hybrid representation, and if we can get the best of both worlds somehow.
Let's take a look at how neural fields can generalize by learning from data. Let's motivate the need for generalization with a few questions. To reconstruct a 3D scene where only sparse 2D information is available. For example, reconstruct the 3D model of this car from one image. What if we want to represent not just a single object, but an entire category of objects with just one neural network? And what if we want to speed up training by learning from similar examples? Well, the vanilla neural field cannot do any of this because it is not data-driven. It overfits to one signal only. To accomplish this, you need to learn from data. Broadly speaking, there are two general approaches in generalization: conditional neural fields, neural networks, conditional neural networks, and gradient-based method learning. Let's talk about the conditional neural networks first. In vanilla neural fields, the output of the neural network phi depends only on the coordinates x. In conditional neural networks, it is conditioned on an additional observation O. And during training, the network sees many examples of O. The network can then generalize to a new observation during inference. The conditioning variable O is often encoded as a latent variable Z. There are three orthogonal design choices. First, let's discuss the local and global conditioning. Global conditioning. The neural field is conditioned on one single variable Z. In local conditioning, the latent code Z changes with respect to the spatial coordinates. The latent code, for example, can be stored within a Voxel grid. In other words, the global latent code represents the entire object, while local latent code represents a local portion of the object. Let's look at a few examples. One example of a globally conditioned neural field is DVR, which represents a 3D model given a 2D image. The neural field representing the 3D object is conditioned on the 2D image. One example of a locally conditioned neural field is Python. The neural field is conditioned on a 2D image again, but the spatial extent of the image features are preserved. In other words, DVR encodes the image into one single global feature Z, but Python encodes the image into a grid of latent vectors. Similarly, pixel nerve is also conditioned on a grid of 2D features. Looking at these examples categorically, each has an encoder, which we'll talk about next. The encoder maps the observation O into a compact latent representation Z. Each word also has a conditioning variable, whether it is global or local. And of course, they'll have the neural field, which is conditioned on these variables. In this case, the neural fields represent geometry and depth, and similarly over there. Geometry and appearance. Any questions? I know this is a lot of content. Let's talk about the encoder. What is an encoder? Well, the encoder is concerned with how to obtain the conditioning variable Z given the observation O. And why do we need an encoder? In previous examples, the neural networks are conditioned on images, but it's infeasible to provide an image directly as the input to a neural network. We need to collapse the dimension of the observation, thousands of pixels, into a much smaller vector that neural networks can handle. An autoencoder does exactly this. A large image can be encoded into a compact latent vector and then provided to a neural field as a conditioning variable. And for images, the encoder is often naturally a convolutional neural network. Now, an autodecoder does not involve a parametric encoder E. Instead, the conditioning variable Z is obtained via joint optimization with the neural field itself. The advantage here is that it does not introduce additional parameters and can be more robust in some out-of-distribution scenarios. So both approaches allow us to obtain a compact representation of a high-dimensional observation. Finally, let's talk about how we can supply the conditional information to the neural network. And there are two paradigms, conditioning by concatenation and then hypernetworks. Since MLP neural networks are domain agnostic, we can simply change the input dimension to accommodate arbitrary input size. We simply concatenate the conditional variable with the coordinates along together as an input to the neural field. Very intuitive. And alternatively, we can also use a hypernetwork, which is a neural network that predicts the weight of another neural network, in this case, the neural field at the bottom. Both approaches can be applied to tasks such as learning entire categories of shapes. In summary, local and global conditioning is concerned with how the conditional information is spatially distributed. The encoder is concerned with how to compress a high-dimensional observation into a latent vector. And finally, hypernetworks and concatenation are the two ways we can supply this conditional information to the neural network. And we can see through these examples that neural fields are compatible with a suite of well-studied deep learning techniques. Finally, we'll briefly talk about a different paradigm for generalization, which is gradient-based meta-learning. Our goal here is still to generalize by learning from data. During training time, the neural network learns to represent the entire category of shapes. During inference, we can obtain an instance-specific representation very quickly with just a few steps of gradient descent. The meta-representation holds the general knowledge about the entire class of data, and from which we can specialize to a single instance quickly. You can see the meta-representation shown here can adapt to very specific instances very quickly. These are the optimization steps to stochastic gradient descent. This wraps up how to generalize neural fields and learn from data. I think we are running slightly behind on time, so we'll allow one question if there's a further question on this. Great. It's a natural place for us to introduce the general framework for using neural fields to solve inverse problems. We first sample the coordinates, which are the inputs to the neural field. The neural network then predicts the reconstructed signal, and the reconstruction is then rendered into what we can measure with real-world sensors. In inverse problems, we are given sparse, noisy, and dimension-constrained information from real-world sensors. However, we want to recover the underlying rich representation from these limited observations of the real world. For example, how can we reconstruct 3D geometry from sparse 2D images? We need a differentiable function mapping those reconstructed signals to the sensor signals. And this is differentiable forward map, the topic of this section. In visual computing, this is called the differentiable renderer. With that, we can now supervise the learning of the reconstructed signal with limited sensor signals. Let's look at a few examples. We can render an SDF via sphere tracing and obtain screen space normal map and depth map. We can volume render a radiance field into an image. We can perform meshing operations on an SDF to obtain a mesh. And we can transform CT or MRI images into raw sensor scans via radon transform or Fourier transform. In the middle column here is our forward mapping function. This is the complete picture. The key insight here is that finding a new application in neural field research is equivalent to defining a new forward mapping function connecting two domains that have never been connected before. A particular type of forward map is differential rendering, which is particularly of interest to us. This enabled the reconstruction of 3D signals from 2D images only. Differential rendering itself is also an umbrella term, including volume rendering, surface rendering such as sphere tracing, as well as neural rendering generally. These rendering methods come with its own benefits and trade-offs. For more details, please come back to this very same room 3:30 today, where another state-of-the-art report will dive into more detail on neural rendering. Finally, let's talk about how to edit neural fields. Classical discrete representations have well-studied editing operations, such as images. For example, meshes can be designated and voxels can be subdivided. But neural fields are not easily editable. For example, a simple Gaussian blur on an image isn't even well defined if the image is parameterized by a neural field. We can't perform convolution on an MLP neural network itself. In order for neural fields to become a mature data format, we must have a collection of well-studied, well-established, and well-defined operations for interacting with the data it stores. And so far, this has been understudied. Although limited, there are some ways to interact with the neural field after it has been trained. We can transform the input coordinates, therefore changing the geometry of the spatial domain. We can do so via explicit geometry, explicit shapes. We can do so via another neural network that outputs, that predicts some sort of displacement or warping. We can also manipulate time, speed up time, slow down time, reverse time, if time is the coordinate. We can also edit neural fields by editing the network parameters themselves. If we have a conditional neural network that we talked about just now, we can change the latent code, or we can change some other explicit conditioning variables. We can also change the neural network parameters by using a hypernetwork obvious stochastic gradient descent or fine-tuning to a specific example. Let's look at more specific examples of each. Here's an example of explicit shapes, which offer a convenient handle for geometry manipulation. And here, the explicit shapes are bounding boxes. This allows us to duplicate, scale, rotate, translate as objects. The kinematic chain of human skeleton is another explicit handle to which we can edit neural fields that are conditioned on this skeletal model. This makes it possible for us, for example, to animate human beings, human avatars. We can also directly edit the trainable parameters. In articulated SDF, the neural field represents a sign distance function, and the neural field is conditioned on the latent variable, latent shape vectors, as well as explicit joint angles. By changing those parameters, you can create new shapes and new articulations of those shapes. Again, you can see there are some constraints, but there are ways you can manipulate and edit neural fields after it has been trained, but they're very domain specific. So this wraps up the techniques for neural fields. More details in the latest developments, please visit our project website and use the search and filter functionality so you can create your own reading list with the latest papers. Questions? Well, we'll take another short break looking at the project website. Our website also allows you to build a timeline of papers that you're interested in. And by default, you can see all the neural field papers chronologically. But you can also click on the title and visit a paper's homepage. The entire timeline can be intimidating, so you can filter the papers similar to the ways we've shown before. By time, by code, whether it has code, whether it's peer-reviewed, and by keywords and authors, so forth and so on, to create your own visualization of the development of a particular topic. With that, we wrapped up techniques. We now move on to the applications of neural fields. Neural fields is a highly active area of research. The state of the art changes very, very rapidly. And the focus of this section is more so showing what kind of applications neural fields can enable, while the state of the art will inevitably change in the future. One of the most popular application area is 3D reconstruction of geometry and appearance. We have discussed examples of 3D reconstructions throughout this presentation, and the next STAR session will also dive into more detail. So we'll move on to the next topic of digital humans. There are several categories of works in digital humans, including reconstruction of geometry and appearance from single images, animatable human avatar, including body, as well as faces, reconstruction of human hands, and surface registration. Why are neural fields particularly suitable for representing humans? Well, first, humans are very complicated. If we open our mouth, the topology of our body changes. Humans are also highly articulated. There is also a large variation of clothing and their appearances. And finally, our skin exhibits subsurface scattering, and our hair has fine structures that are hard to model and render. Meshes, for example, are especially bad at handling large variations in topology. Neural fields, point clouds, and voxels are not affected by topology changes, but neural fields are orders of magnitude more compact in memory compared to point clouds and voxels. And finally, neural fields are compatible with data-driven techniques which are suitable for modeling and learning large variations in human topology, articulation, and appearance. Nerve is one of the many recent works on digital humans. You can learn a 3D volumetric representation of humans from a single digital camera. Again, monocular reconstruction. The work uses many techniques that we have discussed so far, including learning from priors, warping, spatial transformation, things like that. Look at it in more detail. For example, to handle the temporal variations in the articulation of human body, human nerve transforms the coordinates from the observation space that's available with the sensor measurement to a canonical T-post space. This is done with the help of explicit geometry of human skeleton. This takes care of the rigid motion. And to model non-rigid motion, a neural warping field here predict the residual displacement of delta x. And together, these two components allow us to find correspondence between the time-varying observation space and the time-invariant canonical space. In doing so, we can aggregate information across time as we observe the human subject from different perspectives. And there are two important roles neural fields play in this work. First, the neural warping field, which is defined for every point in space so that it can model fine-grained, non-rigid motions. And the neural radiance field, which predicts the human appearance. Now let's take a look at the neural fields for 2D images. In local implicit image function, the image is represented by a two-dimensional neural field, mapping pixel coordinate to RGB color. The application here is super resolution. This is a fantastic example for showing just the continuous nature of neural fields and its inherent smoothness, regularization prior. Look at it in more detail. It is fair to ask, why can't we just interpolate over the discrete representation, which is the array of pixels? As we can see here, there are obvious artifacts related to the discrete grid. Furthermore, neural fields can leverage data-driven methods to infer fine-grained details, such as the window over here. Here's another perspective. Because neural fields are continuously defined for all coordinates in space, to achieve higher resolution, we can simply query the network at a finer resolution, of input coordinates to achieve super resolution. Note that the ground truth that's available for this work was only 32 pixels in resolution.
Now we'll talk about generative models which are enabled by neural fields. State-of-the-art architectures on 2D generative models are mostly based on things like convolutional neural networks of some sort. One example is StyleGAN2 and StyleGAN1. Extending these architectures to 3D, however, has been greatly challenging. This is because of the same dimensionality explosion that we see with digital signals. 3D convolutions are expensive, use lots of memory, and hence the resolution of 3D convolutional models are severely limited. For example, in this case, a 64 by 64 by 64 3D voxel space. Neural fields, in comparison, being a relatively compact representation, can offer some solutions. In this work, for example, from DuPont, they build a generative model over neural fields by generating parameters of the neural fields directly. So there's a neural network or some kind of model that basically generates the entire parameter space of neural fields directly. And this is only possible because of the compactness, parameter efficiency of neural fields. And this is also agnostic to the type of data, so it can parameterize things like images, sign distance functions, or even spatial data on a globe. In generative radiance fields, this is another example. They build a generative model over latent vectors, which conditions a neural field model to learn multi-view consistent generative models for 3D. And in this work, they show that these fare better, much better than voxel-based representations. Another example, in EG3D, they leverage, in this work it's kind of unique because they leverage the powers of 2D convolutional generative models for neural fields. In this case, StyleGAN for neural fields. Thanks to the input agnosticity of neural fields, where you learn basically that neural fields, even if you increase the input dimension space, it's very relatively low cost. They basically, in EG3D, leverage this factor to use the feature maps from StyleGAN, so those convolutional feature maps from StyleGAN, to essentially as a feature grid for neural fields. The neural field basically takes different components of this feature map, expressed as a triplanar texture map, and then basically decodes these feature maps into multi-viewed rendered images, which are then discriminated by the StyleGAN discriminator. With this approach, they are able to retrieve multi-view 3D reconstructions of faces which match the quality of StyleGAN and showcase the flexibility being really beneficial here. Yeah, just to reiterate, this StyleGAN generator generates these 2D feature maps, and these can be just a pre-trained StyleGAN2 convolutional neural network architecture. They use these as triplanar texture maps for this neural field, which then queries from this triplanar texture map to different points in space. And basically does learn this neural field. Again, features to these 3D consistent multi-view images. There are also works which leverage the power of text-driven models like CLIP, which can yield the semantic loss between text and image. Text-to-mesh, for example, uses this to learn neural fields which parameterizes the displacement and texture field for meshes in UV space. This kind of model can constrain the mesh, conditional on text extrusions, and may become very important tools for computer graphics and content creation in the future. There are lots more very exciting neural fields generative models being released every week, so you should definitely check them out all on our website. Neural fields can also be used for all sorts of different applications beyond visual computing as well. As one example of this, let's take a look at topology optimization. Topology optimization is the task of finding the stiffest structure within some material budget for some prescribed load. In this case, you might have some kind of load that you want to support on the left side of this. So the way you want to find a structure that can support that load with the most optimal material configuration possible. Traditional methods for topology optimization generally rely on some sort of mesh structure or grid structure to solve this optimization problem. But to get good results, you usually need to use a very high resolution grid sizes, but doing this optimization at high resolutions can be prohibitively expensive. In this work, Dusti et al. Use a neural network to parameterize the density field and solve the topology optimization through differentiable programming. What is notable here is that to get the gradients of this topology optimization problem, they actually still use a coarse grid-based solver, but the key word here is coarse. They basically find that if they do this solve using a very coarse solver, the results that they get from this neural field-based solve actually matches the result of a very fine, high-resolution voxel-based solver. That is basically the high-frequency bias that they can obtain through adjusting the sigma parameters of some positional encoding function. This basically allows them to solve this problem at very high resolutions, despite the fact that you're using a coarse voxel-based solver to get the gradients of this. We think this is super exciting work that deeply combines topology optimization with neural fields technology. We'll show also another quickly example of using neural fields for applications beyond visual computing. Astronomical interferometry is the process of using a collection of small telescopes located around the globe, which you can see on the top right, to an image that can basically usually only be imaged by using a very large telescope, which is super expensive and also extremely difficult to manufacture. This is a very sparse problem where the coordinates at which things are measured do not fit really nicely into an integer grid. It's just like telescopes located scattered around the globe. And this basically requires strong regularizations and prior to solve. And this might kind of hint at why neural fields might be useful. In this work, they basically use a transformer model which can convert these sparse spectral measurements from each telescope into a feature which can condition the neural fields model via film conditioning. They use a transformer model because they are permutation invariant, and they're very suited for this kind of sparse measurement, which don't really have any kind of ordering, but there's a sequence of different telescopes basically. They basically train this transformer plus the MLP model on a data set of 20,000 imaging examples to learn a data prior to perform this really challenging reconstruction problem. And they basically find that this kind of neural field approach does in fact do better than traditional methods, and also even convolutional neural network-based approaches, because of the nice prior that neural fields also enable, and a data prior they can also learn with them.
Very briefly, neural fields have also been applied to tasks in robotics. In neural descriptor fields, we are interested in teaching robotic gripper arm to grasp and place the mug on the rack. The neural field takes as an input a 3D coordinates as well as a latent vector encoded from the object point cloud. The outputs are occupancy, as well as features for downstream gripping tasks. The gripping features are defined for all points in space. The neural field can generalize to new objects in unseen poses. Again, the state-of-the-art will continue to evolve very rapidly, and for more details on the latest developments in applications research, please visit our project website. And this brings us to conclusions. Not more. During our review, we've noticed several salient trends in neurofields research. Neurofields and traditional discrete representations both have their strengths and benefits, as our gentleman here mentioned earlier with a great question. A large corpus of work focused on finding clever hybrid representations that combine their strengths. This has led to many improvements in computational efficiency, representation capacity, and editability. Due to the iterative optimization required for learning neurofields, the computational cost of neurofields is very high and often prohibitive. Reducing the computational budget makes neurofields more practical in real-world applications. Research in deep learning has largely been driven by empirical success rather than theoretical foundation. In order to better understand neurofields, we need to understand the properties of neural networks themselves better. And the collection of work has started to answer those questions. Some preliminary work suggests that neurofields can also be the new standard for storing data of many domains, due to its impressive memory efficiency, which has also been studied. And finally, the ways we can edit neurofields and interact with them are very limited, and the collection of works have offered some editable neurofields in some restrained ways.
To kind of conclude, in this presentation, we highlighted many of the strengths and weaknesses of neural fields. Like, for example, for strengths, things like compactness, regularization, it's also domain agnostic. But we also highlighted many weaknesses, like it's very computationally expensive. It's things like the spectral bias that plague neural networks. It's not very easily editable. It's also hard to model semantics and discrete data. We kind of also see that there's like kind of a lack of a theoretical understanding of all of these different components that are typically used in neural fields. We also showcased a taxonomy of different techniques which are used to address some of these weaknesses. These include things like architecture, hybrid representations, generalization, forward maps, and editing. Note that many of these techniques may solve a specific problem in isolation, but not necessarily all of the problems all at once. So no solution is an end-all solution to neural fields. Therefore, these techniques only define an extremely large design space of neural fields, which consists essentially of a Cartesian product of all these different components. We hope that our taxonomy of different components of these neural fields can help navigate this really broad design space. We strongly believe that a lot of neural fields applications research should be a systems one. Neural fields as a research community struggles from the growing pains from the speed of progress, and there are frequently both overlapping research as well as a tidal wave of research papers coming out every single day. This is all the more reason to write our papers like systems papers, where we thoroughly evaluate the design space and justify why and how we arrive to the specific point in the neural fields design space that makes our applications really shine. Of course, to do this, you need a design space. And through our taxonomy, we sincerely hope that we have provided a basis function to define this neural fields design space, along with a website that can help you navigate the swarm of papers that exist, and increase both the quality of research as well as the evaluation of works in this space if you're like a reviewer. Covered on a lot of these different techniques in our presentation today, but we will also have a tutorial session at CVPR 2022, where we have a full day tutorial where we will go into much more detail on each of these components and really dive deep into each of these components in much more detail. So if you're interested, you should definitely come check this out also.
We invite all of you to join us. If your paper is missing our database, it takes less than 2 minutes to submit it. And we welcome you to join our community of moderators of this database. We have one final video for you showing just how easy it is to add a paper to our database. I'll step up. I just typed very fast. This is a Google form, very simple, just 2 pages. Click through, select the keywords that relate to your paper, submit, and then we'll do some magic on the back end. And next day, the paper pops up on our web page. You click through, and everything will be there for you to review. The report is not possible without all the authors. This is the last slide, I promise. You guys can go. Thanks to all the authors who actually wrote those papers and provided those amazing works. We also want to thank the creators of Minicomp, which is the backbone of our project, our website database. And thank you to Yixin Jie and Sunny Li for critiquing our report, as well as the website. Of course, our funding agency. And finally, thank you for being an attentive audience. We will welcome any more questions.